So, in this lecture, we will learn how to do privacy auditing. And privacy auditing, in a way, is the first time where the two main components of this course, the attacks and the... שניהם אמורים להיות אותו דבר, אבל רגע... לא, הקישור השני הוא לא מהאתר, הוא פשוט זה. הוא פשוט, זה הקופי זה הקודם. שנייה, עכשיו פתחתי הרשאה לכולם. טוב, הנה נתחיל שוב. אוקיי. So, this lecture, we will cover privacy auditing. Privacy auditing, in a way, is the first time in this course where the two main components meet, the attacks and the privacy protection. So, just trying to recap what we did so far. So we started with taking the adversary's perspective, and we said, okay, how can we attack all sorts of mechanisms that are potentially private? So we found attacks that are specific to k-anonymity, we found general attacks, reconstruction attacks, we covered the most general attack in the case of the most powerful adversary, which is membership inference, basically. And through the membership inference attack, a new definition sort of naturally arise from first principles, which is differential privacy. So now we can ask ourselves, okay, so we have a definition and we know how to prove that a certain mechanism is differentially private. But how can we prove that a mechanism is not differentially private? And in a sense, the hypothesis testing perspective that we saw in the last lecture provides the most natural answer. So let's look at this plot, for example, and recall how did we define privacy. So we said the following thing. Epsilon delta dp basically defines two lines in this ROC plane, where again the ROC plane corresponds to the ROC between any two distributions defined by neighboring data sets and the mechanism. And it states that for any mechanism, which now defines an ROC, it is epsilon delta dp if that ROC is upper bounded by this linear line corresponding to epsilon delta. So that allows us to ask for any given ROC and fixed delta, what is the epsilon of the mechanism, or the other way around, right? So here we have two ROCs. It doesn't matter, to which mechanism and which data sets they correspond. Some pair of mechanisms, some mechanism and some pair of data sets. So right now, with the actual values that we have here, which are, delta equal 0.5 and epsilon equal 1.2, whatever, a number. Is any of the ROCs epsilon delta dp for these parameters?
Considering it's under a privacy band, it must be.
No, so I'm asking for these, is it epsilon, so is it 1.2 comma 0.05 dp? Not is it epsilon delta for some? This is a visual question. Right? Does it seem like these ROCs are okay or not?
Yeah, number 2 is questionable.
Okay, maybe it's because you're sitting far, it's still, like it shows it to be still a bit below. Yes, so they're both okay. This is still not a privacy proof because this is the ROC corresponding to a particular pair of data sets. But if somehow I manage to convince you that these are the worst data sets in some way, meaning these are the data sets that induce the ROC that is the furthest away from the diagonal, then if even that pair of distributions still has an ROC that's below this line, we're good. So we can also ask not only is this mechanism 1.2 comma 0.05 dp, but actually you can ask for a particular delta, what is the epsilon of the mechanism? Or the other way around, for the particular epsilon, what is the delta of the mechanism? How do I do it? So I can just do it visually. Of course, it won't be accurate, but just to get the sense. Okay, so I can play with the epsilon, right? And I ask myself, what is the lowest epsilon where it only touches the ROC curve? So visually, I put it at, I don't know, 0.88. Again, this is, of course, not a way to do math, but it gives us the idea. Right? So clearly, for this particular fixed delta, if I move epsilon to be higher, then it's of course okay, and I move it to be about, again, 0.88, then it exactly touches the first ROC, the red one. But still, the green one is better. So I can, move it further, and I would get, I don't know, something like 0.59. Okay. So, and of course, just to make it clear, I can flip it around. I can have some value epsilon. Let's say here the red one is not epsilon equal 0.76 and delta 0.05. The red one is not, because you see it's a bit above, but we can ask for this fixed epsilon, what is the delta, and I don't know, it's 0.07 or something, right? Just to have a clear idea. And ROC, assuming this is indeed the worst ROC, automatically defines the connection between epsilon and delta. This is basically epsilon is a function of delta, delta is a function of epsilon, and how is it? We fix one of them, we move the other, and we take the minimal value that is still an upper bound. Okay? This is what we got from the previous lecture. So now we can see it in a concrete example. So let's say these are two Laplace distributions. Okay? And here I'm telling you a secret. In the case of Laplace, and in fact, in case of most typical noise addition mechanisms, the worst case neighboring data sets are data sets that differ in a single element that is, let's say, 0 versus whatever is the maximum, the range of the value. So let's say the elements are between 0 and 1. So the neighboring data sets that induce the highest privacy loss, the worst ROC, is the data sets that are like some data set in a 0 and another data set in a 1. And in fact, it doesn't matter what the rest of the data set is, so it can even be just a single 0 and a single 1. It's the same. Okay? So this is the scale, okay? Right? We see here they're further away from each other, and here they're closer, or again, reminding you, since this is sort of invariant to scale, so if I keep the distance between the two distributions and increase the variance, or keep the variance and decrease the distance, it's the same. And for each value, I get a different ROC curve. Okay, so I fix this ROC curve. This is scale is 1, and now I can compute epsilon. Right. So now I'm choosing only a single line instead of two, just for simplicity, because most of these mechanisms, the noise addition is symmetric, and I don't want to get into the extra complexity of what if it's not. The answer is actually, it's the worst case over both directions. So for simplicity, we have a single line. So what happened here? So here we have delta equal 10 to the minus 15. For all intents and purposes, this is 0. And what do we see? The mechanism is 1 comma practically 0 dp. And we know that matches what we expect from Laplace. If your scale is 1, your epsilon is 1, right? And it doesn't matter if we increase delta up to a very extreme range. If we increase delta by much, then epsilon starts to get even lower, right? A Laplace mechanism for a large enough delta has epsilon that is a bit below its worst case, right? Because I have this slope. Right? But if I take delta to be 0, then I still have the pure dp. Right? Nothing is supposed to surprise you. This is just, in a way, completing the story of the definition. So if I started last lecture from the attack and formalized it as an ROC, and then finally said, well, a bound on the ROC would sort of capture what privacy is, and then realize that this is describable by the epsilon and delta parameters, so now I'm sort of doing the other way around. Well, if I got a specific ROC, what is the epsilon delta trade-off? Okay, same goes for Gaussians. Okay? We have two Gaussians. Now we know that the Gaussian mechanism is not pure dp, right? So even though the scale is 1, the epsilon, as you see, is quite bad. It's 2.3, and that is for delta equal 10 to the minus 2. If I start moving delta to be smaller, epsilon grows significantly larger until at some point it will become effectively infinity. And again, the other way around, if I increase delta enough, epsilon goes down. You're not supposed to be surprised in any way. You just need to have a sense of what does a trade-off look like now. And I can also move on to a node distribution. Right, so this is the logistic distribution. Logistic distribution has this shape. Okay, it's also sort of exponential, but in a somewhat weirder way. So the top is exponential decay. That is what we're used to, basically, the sort of more like Laplace or exponential. But there's also another term in the mechanism that makes it a bit more complicated. Okay, fair enough. Again, some distribution has some CDF and PDF. And we can ask again, what happens if I add log normal noise? Now, if I want to really make a claim, well, we know what we do. We write explicitly the log probability ratio, right? The ratio of this for neighboring data sets, which will be, let's say, 0 and 1. I have an expression, I take the log, I have something, I can bound it, whatever. There is some privacy analysis here. But also, again, visually, just to understand what happens, I can just look at it. I say, okay, there's a plot, and I can try to check, for example, if it's pure. And it seems like it is pure dp. You see, it doesn't matter what is the delta that I choose until it's like extremely large. Has the same behavior as epsilon, as Laplace. There is some maximal privacy laws that I never cross. Fair enough. Okay. But here's the problem. What do I do if I add a noise that I don't know how to write its PDF or CDF? So let's peek for a moment behind the curtains and understand, what did I do here? Like, how do I have this interactive plot? Well, logistic regression has a closed form PDF and CDF. So therefore, I can call some NumPy or SciPy function that computes. So the two distributions that I have here correspond to what is the PDF in different values of x. And this ROC corresponds to what is the CDF or CCDF, 1 minus the CDF, for different thresholds, because again, in this case, thresholds are the optimal, the optimal decision rule. I mean, actually, it doesn't even matter, because last lecture we saw that we can even, right, numerically, I can even compute the ROC even when it is not monotonic by simply sorting all of the possible values by their log probability ratio. Remember, this was Nyman-Pearson. Nyman-Pearson told us that the optimal decision rule is a threshold and the log probability ratio. So theoretically, it might be the case that, again, I'm choosing a distribution that we didn't analyze. You never met it in the privacy courses, like here's another typical noise addition mechanism. So hopefully we don't have a clear intuition of, like, does the log probability ratio increase, decrease, is the maximum achieved at the extremes, close to the center? I don't care. But the bottom line is, there is some log probability ratio for every value, and if I sort them and put a threshold, not necessarily an X, but on the log probability ratio, I get all the possible points in the ROC, which may or may not have anything to do with the thresholds on the line. But all of this was done because I had the explicit expression for the PDF and the CDF. But what would I do if, for whatever reason, someone came up with the idea of adding two logistic distributions, logistic noises, with even two different noise scales. So two logistics with the same noise scale still have some closed form expression of their convolution. Right? If I'm adding noise twice, then effectively, if I want to understand what is the distribution of the combined noise, it's basically the convolution of these two distributions. So sometimes it's easy. Let's say I added twice Gaussian noise. Well, that's great. We know exactly what is the convolution of two Gaussians. It's another Gaussian. Its variance is the sum of the variances of each of the only Gaussians. So if for whatever reason my process adds twice Gaussian noise, I can analyze it very easily. It's just a single Gaussian mechanism with a different variance. If I added twice Laplace, well, it's not another Laplace. The convolution of two Laplace is another Laplace, but it again has some closed form expression. But not every pair of distributions, even logistic, if they had the same scale, I think they have some expression. But if they're two different scales, there's nothing you can say. The distribution exists, it's well defined, but if you want to know what is the PDF at any given point, what is the CDF at any given point, the only thing you can do is compute an integral. So, how do we have a chance to reason about such a distribution? Like here, what I'm showing you visually is some plot, but obviously the proofs and the analysis will go through doing the equivalent mathematical component counterpart of drawing this picture, and instead of just numerically looking for the point where the line sort of touches the curve, I will do it analytically. What would be the corresponding thing when I don't have an analytical expression? I can't actually compute it in a closed form. I can run numerical analysis and sort of compute and estimate, but I can't say what the number is. But what I can do very easily is run an experiment. So this is what I did here. This is the same idea of what we saw before, but now I don't know how to write analytically the PDFs. I don't know how to write analytically the ROC. But what I can do is I can simply sample, 500 points from each of the two distributions. I get sort of two histograms. I can make all sorts of guesses at different points. Basically, every point here corresponds to some threshold on the X values. So I say any output that is above it, I would guess the blue distribution. Anyone below it, I would guess the red distribution. I would have some true positive rate. I will have some false positive rate. That's a point. This is not necessarily the optimal ROC. some trade-off function. So I can use it to try to compute epsilon in the same way. Right? So now, basically, it's no longer a matter of finding the line that is, what do you call it? Orthogonal? No, not orthogonal. But we know what we mean.
The derivative of whatever.
So it's not sorry? No, it's not parallel. It has a. So it's not about finding that line, because now we have the ROC is just a bunch of, it's a finite number of points. If I have 500 points that I sample from each of the two distributions, overall I have 1,000 points. So there's 1,000 steps here, effectively. And again, I fixed some delta. I found the lowest epsilon that is still above the trade-off function. And this is how do you go? And this is the epsilon I estimated. Okay? So here, what is it? Like tau here happens to be 3.4. Whatever. I don't know if it's the best one or not. I did it. So now I want to estimate epsilon. How did I estimate? Here we have the numbers. Based on that, it says it thinks that for delta equal 10 to the minus 2, we have epsilon equal 1.03. Is it true? Is it not true? So let's think. What happened here? So, going back to our intuition, what did we say? We said that from the perspective of the attacker, when it tries to guess which of two neighboring data sets was used to produce some output, it decides on some decision rule. Decision rule is a function from whatever is the output domain to the bit 0, 1 of do I think it came from data set 1 or data set 2. This is the task of the attacker. So in this case, the attacker effectively decides, let's choose the threshold 3.4. Maybe a good choice, maybe not a good choice, but it's a choice. And now we know that if we run this experiment many times, the success rate of the attacker on when that it will guess yes when it came from the positive distribution is larger than the probability that it will guess yes when it came from the negative distribution by some gap, and that gap corresponds to epsilon and delta. These are the two events that we have. Okay, so basically what we're doing here is effectively we're saying, look, you told me, you the privacy officer, the one who gave the certificate that this mechanism is okay and we can release it. You claim that this mechanism is something comma something dp. By that, you are guaranteeing that for any pair of data sets that I, the attacker, will choose, and for any decision rule that I would pick, if I run this experiment many times, my success rate won't be very impressive. So let's see. So any point here corresponds effectively to the following experiment. So here's an experiment we ran. Notice what we're doing now is I'm sort of telling the story of the previous lecture backwards. This is what we saw in an early stage of the lecture. We basically realize everything becomes just a 2x2 matrix. And then we built on it gradually and we got to the ROC curve. But once I pick a point in the ROC curve, which corresponds to a decision rule, this is what I have. So I'm just running an experiment. So now we see the same experiment as before, it just chose the same seed just so we have a clear idea. So let's see, I'm jumping a few experiments every time, otherwise it will never end. So here we have, I don't know, six experiments already. 3 of them came from the truly came from the positive distribution and were guessed negative. 2 of them came from the negative and were guessed negative, and 1 came from the negative distribution and was actually guessed positive. There's a false positive rate is greater than 0, but the true positive rate is still 0. True positive rate is this. Okay, but this is just the beginning, so we won't say too much about it, right? And it keeps jumping as I keep adding. And then, as I continue, the point moves with every experiment until it reaches a point. Now, it doesn't reach a point in the sense that it necessarily converges. I just ran a certain number of experiments. I completed the experiments, and then I put the line. And that was my epsilon. So, on the surface, you can think of it as saying, look, I never needed to know the distributions. No, I didn't need anyone to tell me this is the PDF. I didn't need to compute Nyman-Pearson lemma. Could have done something much simpler. Just sample a bunch of times from this distribution, sample a bunch of times from that distribution, and I'll compute have a decision rule, guess, fill this table, and that's it. I just compute these 2 ratios and see what is the slope of the line that crosses this point.
Do you need a check for every decision rule?
Sorry?
Do you need a check for every decision rule in that case?
Okay. So, basically, and I won't go into full details here because we'll discuss it later, but basically what you're saying is the following thing. Differential privacy is defined with a bunch of quantifiers that are all for all. Right? That is the property. So it's for all neighboring data sets, and I picked a particular pair of data sets, and it's for all subsets of outputs, which now we know correspond to a decision rule, right? Because the subset of outputs is the subset of outputs where the decision rule guessed yes or guessed no. Okay, so you're absolutely correct that I can't use this as an upper bound in epsilon, but as a lower bound, I'm fine. And this is privacy auditing. Privacy auditing says the following thing. To prove something, right, the same way we're used in math, that to prove existence, you just need one example. To prove it for all, you need to do math. But it's the same thing here. If someone claims that a mechanism is some parameters dp, it's a for all claim. It says that regardless of the pair of distributions you'll pick, the pair of data sets you'll pick, regardless of the decision rule of the analyst, it can do the most sophisticated decision rule. It would never be able to exceed some relative success rate. Well, to prove that, I need to identify the worst case. So for example, as I told you before, if the mechanism is the Gaussian mechanism, and all of the elements are bounded within radius 1 L2 ball, even if it's high dimension, well, I know that I only need to consider the pair of distributions that are Gaussian around 0 and Gaussian around 1. I don't need to worry about the various dimensions. I don't need to worry about the identity of the rest of the elements. Life is easy. Okay? So I know what the pair of the data set is. Had I not known, I would have had to prove something about for any pair of data sets. Same for the decision rule. In the case of the Gaussian, we know what is the best decision rule. The best decision rule is, for any false positive rate, is a threshold and the x's. Okay, so we know how to achieve a point on the worst case ROC. So we can both numerically, but we don't need to do it because we can do it analytically. We know what the CDF of the Gaussian is, etc. And we have a closed form, to the extent that the distribution of the Gaussian is closed form. Closed form expression of the privacy guarantees of the Gaussian. Same goes for Laplace, same goes for other mechanisms. But what if the mechanism is some, neural network? Like the output is you put in a data set and you get as an output a model. Right? It's the training process. The randomness comes from the stochasticity of SGD. Or, I can come up with a ton of examples. Like randomness is very common in the computer science literature and practice for many different reasons. We sample a subsets of the rows of some matrix. We sample a subset of the nodes in a graph. We do all sorts of stuff. So here's a random mechanism. And someone might come and say, hey, I think this is very private. I think this is 0.1 comma 10 to the minus 10 dp because it's very random and it's very hard to find out what's going on. I don't necessarily have a way to analyze the two distributions because most of the random things we do these days, we don't know to write explicitly the distribution over whatever it is that we output as a function of the input. But I can always run this experiment with some pair of data sets and some decision rule. And in that case, I have a lower bound, right? This is not an upper bound. Privacy proofs provide an upper bound. I prove that something happens for all data sets, for all decision rules, etc., etc. And then I have an upper bound, which also might not be tight. Now, in the proof, it might not be tight because I didn't know how to analyze exactly some complex expression, and I used some inequality that log 1 plus x is bounded by x, whatever. And I lost something maybe. That's why upper bounds might be loose. Empirical lower bounds, and this is not. We also have in some cases theoretical lower bounds. But this is not a theoretical lower bound. This is an empirical. I ran an experiment, and this is how much I succeeded. You can't tell me that I'm nearly perfectly private if my true positive rate is so much better than my false positive rate.
Is that also probabilistic point in a certain way because the mechanism is probabilistic?
Okay.
It might have given me really bad outputs, even though in general it's really good. Just because the randomness gave bad output, not because the data is bad. Normally it would be good.
Good point. So effectively what you're saying is, had we known the exact true positive rate and false positive rate, if we wouldn't have had numbers here, if we would have probabilities here, corresponding to the exact probability that a mechanism and a decision rule and this and would land in each one of those four, then I know where is this point, where does it exactly belong, right? It's a point on the ROC that maybe I don't know to draw analytically the ROC, but at least I know it. And then I can compute this slope, and then I have a lower bound, and I can trust that lower bound. There is no probabilistic aspect to the lower bound. This is math I'm doing, not statistics. But as you're saying correctly, not only that this is not necessarily tight because it's only a lower bound, I also can't trust it as a lower bound because I ran an experiment. And we know that we never trust an experiment as a perfect representation of the underlying distribution. So what you're saying now, and is correct, is that privacy auditing has another layer of complexity, which is exactly the next point we're going to touch on. But just before I move there, I want to formalize what we have said so far. So far we said the following thing. I'm trying to complete the arc. So we started last week with defining differential privacy by taking the adversary's perspective. We said from the adversary's perspective, if it's the most powerful adversary you can consider, which is one that knows everything but a single bit of information, which is, did I participate in the data set or not? So it lives in a world where it needs to consider only two possible worlds. It doesn't have infinitely many options, only two. This data set with me, this data set without me. And then it gets some output from the mechanism, and it needs to make a guess. And again, only two options for the guess. So that's why it's a 2x2 from its perspective. And then we realize always finding a point on the, guessing a point on the diagonal is trivial. And it wants to move further up, further to the corner as much as it can. And basically, the further it can be from the corner, the less private the mechanism is. And we decided we will use these lines to express this bound, which turned out to be dp. And now we're going the exact way back. So we're saying, okay, so if I do have an ROC coming from some mechanism, that tells me what is the privacy of the mechanism. So if I know that this ROC is the worst case ROC, correspond to the most distinguishable data sets, then I can trust it not only, and I know what is the best decision rule. Let's say I computed the Neyman-Pearson lemma. So now if I have a point, right, when we had a point here, this is not a lower bound. This is an exact value of the Gaussian mechanism. In this case, I can tell you for sure that the Gaussian mechanism with scale 1 is 1.01 comma 10 to the minus 09 dp up to whatever numerical stability. Why is that? Because I know that all the quantifiers throughout the way, I indeed chose the worst case. The worst case neighboring data sets for the Gaussian mechanisms are a data set with mean 0 and mean 1, or sum, whatever. The worst case decision rule is a threshold on the x's. So this draws the entire curve. And then once I fix the delta, I found the point, there is some threshold here that corresponds to the worst case epsilon. So this is not a lower bound or an upper bound, this is an exact expression. But once I move to an experiment, now I don't necessarily know that these are the worst case data sets. It makes sense because typically noise addition, the further away the means are, the easier it is to distinguish, but theoretically it might not be the case. Also, here I chose a threshold on the x values, but I definitely can't claim that I know that the low probability ratio is monotone in x. So I don't know, but what I do know is that this is a lower bound. But as you said, this is not even a lower bound because I could have just ran the experiment again and again and again, and every time get a different number. So besides all of the limitations that I described so far, we need to account for another aspect, which is we actually did statistics, we did an experiment, and the correct lower bound will be one that also takes that into account. Okay, so let's have a break.